Let's look at what happens to energy in a simple harmonic oscillator. Little clarification. Up to now, what I've tried to do is I've always tried to make my mass spring systems horizontal. So we'd have a frictionless surface and the mass would oscillate back and forth about some equilibrium position, and that equilibrium position would be where there is no force in the spring. Force would be 0, and we'd measure our displacement from that equilibrium position. And when we did that, the energy stored in the spring, the potential energy of the system, would be that elastic potential energy stored in the spring, and that would equal 1/2 kx squared. Now it turns out, and I'm not going to show it mathematically at all, but we would like to note this because, of course, vertical mass spring systems are much more common and much easier to do than horizontal mass spring systems. There is, of course, going to be gravitational potential energy in a vertical system because the object's moving up and down. But there will be an equilibrium position, and it won't be the same equilibrium position as here where the spring is unstretched. The equilibrium position will occur here when the force from the spring exactly balances the weight of the object. So that right here the net force would be 0, and we'd call that our equilibrium where x equals 0. And then of course the object's going to vibrate back and forth, and we'd call that displacement x, and it would get up to a maximum value x0, which we call the amplitude. Now it turns out that the potential energy of this spring, and when I say potential energy I mean the sum of the elastic potential energy stored in the spring plus the gravitational potential energy, will be equal to 1/2 k, still the spring constant, times x squared. So we'll still get the same expression here, even though it's including the gravitational potential energy. And that's really because we've shifted the equilibrium position. It's not anymore at the place where the spring was unstretched. Mathematically, we can treat the vertical spring exactly the same as the horizontal spring. It's not any more difficult to us. In any simple harmonic oscillator, the energy will always slosh back and forth between kinetic energy and potential energy. And our kinetic energy would be given by 1/2 mv squared. As I was saying on the last slide, the potential energy will be given by 1/2 kx squared, even though that will include gravitational potential energy in a vertical spring. And if we add those two together, we're going to get the total energy of our oscillator. So let's make up a number for our total energy. Let's say we've got a total energy of 50 joules. Then what has to happen is you've got to get a maximum kinetic energy right at the equilibrium position. And that's because the net force is downwards here. And then at equilibrium, when we say the displacement is 0, then the net force is 0 by definition. And then the net force is, of course, upwards as you pass equilibrium. So that means the object's going to speed up due to this force on the way down, and then once it gets past the equilibrium position, the net force will be up, causing the object to slow down. So we know that kinetic energy will be a maximum at equilibrium. And we also know that the potential energy will be 0 there. Because in our equation, if we take the displacement as 0, potential energy is 0. So that means our kinetic energy would be the full 50 joules. And our total energy has to be 50 joules. At the endpoints, we know the speed is 0. At a turning point, you've always got 0 speed. And that means your kinetic energy would be 0 here and 0 here. And all the energy would be potential energy. So it would be a full 50 joules here and here at the endpoints. Your total energy remains at a constant value of 50 joules. Of course, that's assuming no energy is being lost due to friction. Your amplitude is not decaying. And of course, if we were to take any point in between, let's say we take a point right about here, then we might have a kinetic energy, say, equal to 20 joules. Your potential energy would make up the remaining 30 joules. so that you got a total energy of 50 joules. But in summary, we can say that the total energy will equal the kinetic energy in the middle at equilibrium, and it will equal potential energy at the endpoints. And as we were saying, the kinetic energy and the potential energy should sum to a constant value, the total energy. And we can kind of see that this here in a little more detail. If I consider the potential energy, so this is my potential energy graph. Of course, at the endpoints A and B, I get that maximum potential energy. And then right in between, that's where I get zero potential energy. And so I get a graph that looks like this for potential energy as a function of time. Now, if I want to consider the kinetic energies, of course, it's going to be 0 at the endpoints. So we'll get zeros at A and B. That's here and here. I get zeros in the kinetic energy. But of course, it's a maximum right in the middle at O here. So then if I add those two graphs together, going across the top, I always get a constant value here for the total energy. This is my total energy. So if I look at the, say, the kinetic energy here plus the potential energy here, they add up to the same value at any point along there, so that my Ke plus Pe is equal to the total energy, which is constant. In this particular unit, I think it's kind of critical that you go over the equations that are in the IB data booklet, see what equations they give you, what equations they don't give you, and the form that they give you them in, and what symbols they use to represent the different variables. So this first equation, you would expect that the angular frequency is equal to 2 pi over the period. And then they give you the displacement equation. This is for an object that is given an initial velocity to the right from the equilibrium position, and there's the corresponding velocity. And this one here, it's an object that has been released from the rightmost position, and then it would execute a cosine motion. What's kind of surprising is that they don't put a negative sign here for the velocity. Of course, if we release it from the right, the velocity, the slope, would be negative here. It's coming downwards, so this should be a negative. Perhaps the IB has defined their variables different than I have. I'm not sure. Maybe this is an equation for speed. I'm not sure. These two equations I'm going to talk about more in a second. These ones here should be semi-familiar to you. Let's start with this one. I usually have been writing the total energy. Of course, they're writing T for total energy. The total energy, it's all potential energy at the endpoints where x is equal to the amplitude. And that means that the potential energy is given by 1/2 k times x naught all squared. And that is equivalent to this expression here. But what they've done is, instead of writing k, they wrote m omega squared. Now that's a good thing, because that tells you, that really gives you the other expression that we had earlier, which was that omega squared equals k over m. So that's very handy. The reason I think the IB did not use a k here was because if you have something like a pendulum executing simple harmonic motion, then there is no spring constant. There is, though, a constant, and it would equal the mass times the angular velocity squared. And then you'll notice that the maximum kinetic energy, which would equal 1/2 m maximum speed squared, must be equal to 1/2 m omega squared x naught squared. So that's kind of handy as well, because you can see here that v naught must be equal to omega x naught. So that's a very handy expression as well. Now let's go back and take a look at these equations here. This little expression is coming from conservation of energy. What it's saying is that the total energy has got to equal the sum of the kinetic energy plus the potential energy. So if I put in my expression for the kinetic energy, I'll just write it as a half mv squared. And my potential energy, which would be 1/2 kx squared, that's got to equal the total energy. And of course, our total energy is equal to the potential energy at the endpoints. So that's equal to 1/2 k, and then take the displacement, where the displacement is equal to the amplitude, so x naught squared. Now what I'm going to try to do is rearrange this equation for the kinetic energy, so I'll get that a half mv squared is equal to 1/2 kx naught squared minus 1/2 kx squared. I'll common factor that half k, so I get a half k x naught squared minus x squared is equal to my kinetic energy. And of course, if I go back, I remember that k is equal to m omega squared. So I can use that expression to say that kinetic energy is 1/2 m omega squared x naught squared minus x squared. So what's this telling me? Well, it tells me I can figure, if I know my displacement, I can figure out what my kinetic energy will be. So it gives me Ke for any displacement. Now this expression, it tells me it's a relationship between the speed and the displacement. So if you tell me where the object is, I'll tell you how fast it's going. We just had this expression that Ek was equal to 1/2 m omega squared x naught squared minus x squared. But of course, kinetic energy is 1/2 mv squared. So I can equate this to this. They have to be the same. So in a sense, they didn't have to give us this equation because we could figure it out from the kinetic energy equation. But it does tell us that V must be equal to taking the square root of both sides plus or minus omega and the square root of that expression, x naught squared minus x squared. So it really doesn't give us any more information than that kinetic energy formula. Okay, so I've got a few sample problems for you. First one, read it over and try the question and then come back for the answer. Okay, so in this question, we're halving the amplitude of the vibration. So we're, instead of having it go the full Monty, the full x here, we're going to reduce the displacement to x over 2. So if we have half the amplitude, hopefully you remember from the other lesson that the amplitude didn't affect the period because we knew that omega is equal to k over m, and omega is related to the period. And if this expression doesn't have an amplitude in it, then the amplitude does not affect the frequency and it does not affect the period. So the first thing is it's got to be either A or B because the period will not be affected. Now the energy is going to be affected, and the energy will go as 1/2 k times the amplitude squared, because at the endpoints the energy is all potential energy. So if we were to half our amplitude here, then let's say our old energy was 1/2 k x naught squared. Our new energy would be 1/2 k x naught over 2 all squared, which is equal to 1/4 of 1/2 k x naught squared, which is 1/4 of the old energy, E. our answer is this one here, B. Okay, another question. Read it over, come back for the answer. Okay, part A. Hopefully you said that omega is equal to square root of k over m. K and m, we know both of those. 16 newtons per meter divided by 1 kilogram, and you're going to get an angular frequency of 4 radians per second. Now we want to find out the speed of the mass when the displacement is 15 centimeters. So our speed, it's a speed, so we don't have to worry about that plus or minus sign in that equation, that plus or minus omega square root amplitude squared minus displacement squared. We don't have to worry about that because it's speed. So this will be 4.0 radians per second. Our amplitude, we want to get a speed in meters per second, so I'm going to use SI units here. So my amplitude was that 20 centimeters, so 0.2 meters. You got to square that and then subtract off the particular displacement, which is 0.15. Square that. Work that all out and you should get about 0.53 meters per second for your speed. And then in part B, you're asked for the potential and kinetic energies at that same point. So the kinetic energy would be equal to 1/2 mv squared, which is 1/2 1 for the mass, and our speed was 0.53. That'll get squared, so we get a value there of 0.14 joules. The potential energy at that same point at 15 centimeters is going to be 1/2 kx squared, so it would be 1/2 k was 16 newtons per meter, and our displacement from equilibrium will be 0.15. That'll get squared. Work that out, you get a value of 0.18 joules. So that would be the kinetic and potential energies. Of course, if you sum them up, you'll get a total energy equal to 0.32 joules. And you can check that out. If I take my expression for total energy, which is 1/2 m omega squared x naught squared in the data booklet, I'll get 1/2. M omega squared is just k, so that's 16. Then you're going to have a maximum displacement, or an amplitude of 0.2. Square that out and you do get 0.32 joules. So those two values check out. And one more question. Read it over and then come back for the answer. Okay, I've written down the given values. The amplitude was 12 centimeters or 0.12 meters. The mass was 1.4 kilograms. Frequency was 2.2 hertz or cycles per second. And so in part A, they asked you for the displacement as a function of time. It was an object that was starting to the right, so it's going to be a cosine to get a maximum positive displacement at the beginning times omega t. Omega, we can work that out. It's going to be 2 pi times f, and that comes out to be 13.8 radians every second. So if I plug in my values here, my displacement was 12 centimeters. Cosine 13.8 times t. Part B, ask for the spring constant. Okay, should be equal to m omega squared. The mass is 1.4. Omega is 13.8. Square that, you get a spring constant of 270 newtons per meter. Part C, is the total energy. I tend to like TE capitals for total energy as opposed to ET, but either works. That's got to equal 1/2 K times the amplitude squared, which is going to be 1/2. Taking my K value to one more significant digit for the calculation, it's 267 newtons per meter, and my amplitude was 12 centimeters. That gets squared. It gives me a value of 1.92. It gives me a value of 1.9 newtons. And part D, my maximum acceleration will be equal to omega squared times my maximum displacement. So that'll be 13.8 all squared times 0.12. That comes out to be 23 meters per second squared. Part E, we're looking for the maximum velocity, which should equal omega times the amplitude, which will be 13.8 times 0.12. And that is equal to 1.7 meters per second. Part F, it's the velocity they want this time. So it was moving to the right, which means it has to have a positive velocity if it's moving to the right. So it's displaced to the right 7 centimeters, and it's moving right, so it's got a positive velocity. So my V will equal the positive omega amplitude squared minus displacement squared. And that's 13.8 square root of 0.12 all squared minus 0.07 all squared. And that should come out to a speed of 1.3 meters per second. And part G asked for the acceleration at that same point in the motion. So acceleration's always in the opposite direction as the displacement. That's really our defining equation for simple harmonic motion. So we'll get negative 13.8 all squared times the displacement 0.07, positive because it's to the right, and that gives a value of negative 13.3 meters per second squared. Of course, that's to the left. That's what that negative sign means. It's stretched to the right, so of course it gets pushed to the left. And that's all for today, folks. Thank you very much.